Hello, this is Arun Agrawal from Indian Institute of Technology, Kanpur. So the talk today I have is Eigenstrain Reconstruction from Contaminated Data using Inverse-EIM. Next slide has outline. Uh, I'll introduce the key applications um, for heterogeneous particulate materials, and then formally I want to describe the HLB's equivalent inclusion method for uniform linear and quadratic eigenstrains. And finally I want to present the reconstruction solution for unknown eigenstrains using inverse EIM and results and remarks. So HLB's equivalent inclusion method is applied to various particulate microstructure materials. For example, we have a foam particle cluster here where you have this density and size is millimeter, and then you can estimate the residual stresses using quadratic eigenstrains. Because of the elastic interaction, the eigenstrains cannot be uniform. This is a good approximation. However, if you want to calculate the exact solution for interaction between two elastic inclusion, then you have to take several higher order terms. So initial solution using polynomial eigenstrains was conjectured by HLB in 1961, then presented by Mustodovidis and Mula in 1975, and several others. So if you have several higher order terms, they do not show good convergence when the order of terms is increased, which poses a very challenging uh, situation. Still, the the EIM has several advantages because it's very intuitive and there are very few unknowns, and when the eigenstrains can be assumed as uniform, very good solution can be obtained. So however, when the eigenstrains are polynomial, um, there is a problem of convergence, and also um, to reconstruct the polynomial eigenstrains, the formulation is an inverse formulation, and there is a numerical instability when higher terms are included. So formally, I would like to describe how EIM works. So in EIM, you have inhomogeneity. If it is elliptic inhomogeneity, you have this material, matrix material, and with applied load, and then equivalent eigenstrain. So in the matrix material. So an eigenstrain is a fictitious term, and it is representing a stress-free strain, for example, a thermal strain. So the essence, the most remarkable feature is that when the applied field is uniform, and this is the inhomogeneity is elliptic, the eigenstrains are uniform, and also the elastic strains are uniform. So you can calculate inside the inclusion, and from solution inside the inclusion, one can calculate the solution external to the inclusion by superposition. Um, so this was in 1957, and then it was also um, further these these terms are further elaborated by Mura in 1987, and then we have all these relationships between eigenstrain and the elastic strain using the concept of distribution strain and SLB tensor. So SLB tensor is uniform when the eigenstrain is uniform, as we saw in the previous slide, and the challenge now is to find the SLB tensor when the eigenstrain is has polynomial terms. So for uniform, we already have this solution. So polynomial eigenstrains are represented as series with coefficient unknown, with let's say prescribed coefficients alpha 1, alpha 2. So when the prescribed coefficient has linear form, we have alpha 1 and alpha 2. When this is quartic form, alpha 3, alpha 4, alpha 5. This is for the x component. For y component, we have beta 1, beta 2, and so on. And then for the shear, we have the delta 1, delta 2. Now solution can be obtained for linear eigenstrains as this. So for linear eigenstrains, we have the eigen displacement, which are quadratic. So this is the expression for complex eigen displacement, and from this we obtain the solution for SLB tensor for linear eigenstrains. So all the terms are linear. Now in the quadratic case, the terms of SLB tensor are all quadratic. So they have quadratic and or they are constants. So these are the coefficients prescribed eigenstrain, and then the SLB tensor has quadratic plus constant terms. There is no linear term. So there are some product terms also. So this was conjectured in 1961 by SLB already, but the solutions came very recently in 2014. And for cubic much later. So the geometric interpretation for this conjecture is that if we have quadratic eigenstrain, it is supposed to induce elastic stresses with only quadratic or constant terms, and not the linear terms. And if you have linear eigenstrains, it is supposed to induce the elastic strains with linear terms and no constant terms and no quadratic terms. So this is the geometric validation for this conjecture. So now we have the unknown eigenstrains. Based on the conjecture, we should only use half series. The problem for the inverse computation of a non-eigenstrain is imposed because there is non-uniqueness and there is data noise. So some framework was already proposed in 2002 and later extended by Korsunski in 2007. So since it is already non-unique, you can omit some components, for example shear, and you have to use one should use reasonable distribution. That is, if the order of eigenstrain is known, then only include terms of with same order, and also terms half series terms of less order. So if the supposing the order is 4, so we have to include 4 and 2 and constant 0, not using the 1 and 3. Here we have a quadratic eigenstrain which is prescribed, and then we use 3 types of data. This is distributed, and this is only in the center of the inclusion, this is only on the boundary, and there are 26 data points. So so this is the elastic field which is prescribed with random noise, so which is the contamination. So noise is in the elastic field, and then we want to estimate the eigenstrains using approximating polynomials. So ideally we will use the only even order polynomial terms, because we know that this is quadratic eigenstrains which are prescribed. So this is in the example we are prescribing EXX and EXY, and then we use 2 reconstruction models. One is without the linear terms, another is with the linear terms. So the results are as this: if we have only the quadratic terms, the error is least as expected for the data type 1 and more data type 2 and 3. But when we have also the linear terms, the error is very much enhanced in the data type 2 and 3, which shows undesired fluctuations, and these sums are supposed to be 0 when there is no data noise. So in agreement with the conjecture. So this is a numerical validation for the Eshelby's polynomial conservation conjecture. Thank you. So I'll just close.